Hi there, and welcome to the Senior Design Group 11 midterm demo. This is the Controllable Autonomous Trash Collection Robot, the CatBot. Has this ever happened to you? You have so much trash in your living room that you can't pick up? Well, it sure has for us. So that's why we invented our trash collection robot to solve the problem. So first is the optical subsystem overview. So we 3D printed a camera holder with a 600 long pass filter, and also are in the process of 3D printing our laser mount with two lenses to do the 60 degree or actually 50 degree IR laser divergence for our flashlight. This is us testing the Raspberry Pi camera laser pointer system. So as you can see on the left, it's modulating, and the raw system on the right is picking that up and returning the X position of the average between two laser dots to our camera system. So what we're going to do with that is we're going to use it to coordinate the angle of approach to our trash collection for the robot. And this is raw, so we can run several programs at the same time. So this is going to be used in conjunction to our LiDAR system, which is going to give like range, radial distance. So here we're showing the display image with what the Raspberry is processing, and the raw image, what the camera sees on the left and right here. They're running at way slower frame rate than what our laser remote is actually doing. But that's our camera system plugged into the Raspberry. We still have to work on powering the Raspberry Pi and getting it integrated onto the drivetrain. But we hope that this is enough to show that in principle it does work. And we have all of the parts printed, so we can start trying to integrate in the next month our actual directional system and programming, which is going to be a huge software challenge for us in the upcoming weeks. So next we're going to show the drivetrain, which is fully functional. Our team member Adam has been working diligently with his stepfather, who does construction. And like metal work. So he designed the entire holder for this system. It needs to go back a little. But clearly he still needs to work on the aluminum cups at the end of the arms, which, as we show later, actually deformed as we're picking up the 2-pound object. But this is us testing the initial servo scoop for our robot and actually getting it to work. We had a malfunction initially that caused the arms to both collide into each other and lurch forward into our electronics, which thankfully didn't cause much because it was just the regulators. Adam here has the pre-store made regulators, and we're running this off of a ESP breadboarded, but team member Griffin is working on getting a ESP into a breadboard design, a PCB design. But we use the breadboard for this because our PCB had a pinout mistake that we have to correct. Additionally, we're using the store-bought regulators, but Adam actually made 3 different types of regulators for our project that he already ordered and had pre-made, but 2 of them ended up not being functional, except for the 5.2 volt one that we have powering our Raspberry and our LiDAR system. But again, this is more testing of our system.
5, 6, 7.
He's counting down how many seconds it takes for the robot to lurch forward and pick up the piece of trash. And so we're just trying to get the servo positioning correct for our robot to make sure that it's absolutely perfect for pickup and everything. But see, this is the first time that I actually picked it up and moved forward enough. But we did an additional extended object pickup routine. On the floor here, we have a 5-foot piece of masking tape that we had the robot follow along with to test our timing of a pickup. This is quite slow. We ran this one very slow to avoid any potential accidents. As I again explain later in the specifications, It's going to take a lot of troubleshooting in the next month to make sure that we can triangulate trash correctly. And that's what our group wants to really focus on, is making sure that the laser system is being detected accurately, which we've already done for the most part, and making sure that we can do object detection and avoidance with our IR laser. So here we are again doing another trial. Another thing we noticed is, as I said earlier, that we have to power the entire system with Griffin's laptop, which will inevitably be replaced with a actual printable circuit board for our design in the final. This is just to show proof of concept, since we've not been able to purchase a USB-C adapter or put it onto our breadboard for the ESP and everything to power the system with the battery, which is fully possible. We have all the regulators connected. We just need to connect the wire from the regulator into the Raspberry Pi in order to start getting fully coordinated vision processing on the robot. So again, this is our test 3. So it does pick up the object with pretty decent success. Griffin programmed this entire initial part, which took a little bit more time, to show that it can rotate back and forth, and that's to simulate the search procedure. So our camera is going to be running in real time while it's rotating back and forth looking for the laser dot, and then what's going to try and do is center itself an angle, and then after it centers itself an angle, it's going to approach the trash, and as you see here in the third trial, pick up a piece of trash. And again, these servos are running quite slow. They could move quite a bit faster. We just were nervous about breaking our servo system and everything, because every time you run something too fast, there's an opportunity to mistake the calibration. So what we're really focusing on with that is calibration rather than speed. But as you see here in the product requirements, the system must be able to pick up trash within a certified time, a specific weight, and the modulation of the frame rate of the camera versus the optic system. So there's our first test of picking up the object. Yet again, here's another trial we ran of picking up the object with our drivetrain in the specified number of seconds. This is, again, 4 times slower than what we actually expect it to be for the final. Or we might have to adjust the specification according to what is acceptable for the overall speed for the drivetrain. I think our group members were just a tad nervous, because we've been working on making this build for quite a bit of time now to run it at full speed, but we did as much testing as we could. So see here, it's still kind of moving a bit slow. Like our average for this 5 foot was 90 seconds. We later ran it again with the dipsticks for the robot, and that actually increased our speed like 4-fold. But we really just didn't want to test it, because we didn't want anything to go wrong for this demo. As you can see, it does do a pretty good job of moving a specified distance. And there you go. Again, just to emphasize that this is quite the process. It picks up the water bottle. Perfectly drops it into the trash can. So the second thing we needed to check was the camera program running with the frame refresh rate of 50 frames per second. So the refresh rate was 50 hertz, as Kobe is showing here. But I actually believe that this refresh rate is actually the half the frame rate. So it's actually running at what I believe it should be 50 frames per second or 50 hertz. So Kobe did the average of this, which was 50.9 with standard deviation, or 50.2 with a standard deviation of 0.35. So for the last part, we did the robot must be able to pick up objects of up to 2 pounds. So again, we're taking the robot, and we actually got a peanut butter jar, which was about 2 pounds.
Okay.
And we had it go over and pick up the peanut butter jar.
Come on.
And as you can see at the end here, it weighs 900 grams or about 2 pounds.
Oh, yes.
I'm counting that. I'm counting.